Hi guys, good evening everyone. Good evening guys, how are you all? I hope everyone is doing well. Hi Ayush. So what we'll be doing today is guys, we'll be discussing about molecular orbital theory and that is from chemical kinetics chapter. So before starting, okay, so it's evening, Ayush. Maybe you are at place where there is a night, okay, but yeah, so let me just quickly introduce myself for all the new learners who are here. Okay, so I'm Manisha Rani, your chemistry educator at Unacademy, and I have enriched 5 years of experience in online and offline teaching. I have completed my masters from NIT Warangal and bachelor's from Delhi University. I have cracked prestigious exams like IIT JAM, CSIR NET and GATE. I have given best ranks through my student, and yes, I am a plus verified tutor, guys. So what we'll be doing today is we'll be learning about the yes molecular orbital theory. So all of you must be knowing that the theory which was given before molecular orbital theory was VBT, and in VBT there were certain limitations. Yeah, hi Akshay, good evening. Very good. Yes, Akshay. So, who and all did it? So, Millikan and Hunt, both the scientists, they actually discovered the molecular orbital theory. So, this was discovered by Hunt and Millikan. Okay, so why it was discovered? Because it was the VBT, the valence bond theory, which was given before it, it was having certain limitations, and to overcome that, molecular orbital theory was given. So, as you know, the name itself says molecular orbital. So, here you're going to take is very good. Yes, Akshay. So, here what we are going to do is we are going to talk about molecular orbitals. So, basically, you all know what are atomic orbitals, right? So, atomic orbitals our SPDF, we have discussed about it. We know that SPDF are the atomic orbital, and from the atomic orbital, what we can do? We can make molecular orbital. Yes. So what it will be, how molecular orbitals are formed, that will be learning. Okay, so obviously for an atom we can discuss atomic orbital, and for a molecule we have to know about molecular orbitals. Now let's just quickly discuss about saline features of MOT, that how MOT helps us to understand about few things. So let's just quickly discuss that. So some features of MOT, how we can relate with it, let's just quickly get to know about it. So what we are discussing now, what are the features of MOT, which is molecular orbital theory. So the first thing is how your molecular orbitals are formed, obviously by the combination of atomic orbitals. So this is what it says, that molecular orbitals are formed by the combination of atomic orbitals of proper symmetry and comparable energies, right? So what we can relate, that molecular orbitals, yes, are formed. First thing what we can relate, how molecular orbitals are formed, but they are formed by the very good combination of atomic orbitals. Now how the combination takes place, that was given, how the overlap takes place, that was given by whom? By the linear combination of atomic orbitals. Very good, Akshay. So molecular orbitals are formed by the combination of atomic orbitals. So MOs I'm writing for molecular orbital, and AO I'm writing for atomic orbital. Okay, so this is the short form that we'll be using. So molecular orbitals are formed by the combination of atomic orbitals of what? Proper symmetry and energies. Proper symmetry and comparable energies. So this is important for us to know. Correct? Very good. Now talking about the next thing, what we can relate. This is chemistry, Ayush. So another thing, when an electron in an atomic orbital is there, it is under the influence of only one nucleus. Because in atomic orbital, we are talking about, yes, we are talking about an atom. But in molecular orbital, we are talking about a molecule. So the electrons will be now in the influence of two nucleus. Why we are learning these features, guys? Because many times the questions are asked, like which among the statement is correct, but like which statement is correct among the following, which is not correct among the following. So we should know about all these points. Correct? Very good. So yes, an electron in an atomic orbital is, in atomic orbital is an influence of one nucleus, yes. While here an electron in molecular orbital, it is an influence of what? It is an influence of two nucleus. Remember that. So this is also important. Your atomic orbital, so in short form, another way we can say atomic orbital is monocentric, while your molecular orbital is polycentric. Yes, it is polycentric because it has more than one center or more than one nucleus. Yes, absolutely correct. Now the third feature, always remember guys, that the number of molecular orbital formed is equal to the number of atomic orbital combined. So the number of MOs formed, the number of MOs formed is equal to the number of atomic orbitals combined. Okay, this is also a important thing. Like suppose if you have two atomic orbital they are combining, so you will get two molecular orbitals only. If say n atomic orbitals are combining, so you will get n molecular orbitals only. Absolutely, very good. Okay, now what we'll be learning, before discussing about that it can accommodate two electrons and what and all rules it follows and everything, let's just quickly relate about it, that how molecular orbitals are formed and how they combine, right? So because we talked about the molecular orbital formed is equal to the number of atomic orbitals combined, but how atomic orbitals combine, that we can learn on the basis of linear combination of atomic orbitals. Yes, so before continuing with the features, we'll be quickly discussing about linear combination of atomic orbitals, like how they combine together. So remember that your atomic orbitals can combine. Yes, how they can combine. So remember that guys, when we discuss structure of atom, in that we discussed that for an atomic orbital we can define a wave function, because your atomic orbital, yes, it is a region present in an atom in a orbit where the probability of finding electron is maximum. So it can show dual behavior and we can define for an atomic orbital wave function. Okay, absolutely, it comprises crust and trough. So suppose if I talk about H2 molecule, so in H2 molecule, what you will be having guys, you will be having two hydrogen atoms. So to just distinguish them, I can say HA and HB, correct? And for them, I can talk about psi like wave function A, wave function B, right? This is called as psi. This symbol is called as psi. This is like Shivji ji ka Trishul, right? So this is psi, which is a symbol for the wave function. Now what you can relate, that whenever a molecular orbital is formed, so suppose your molecule wants to be formed, HA and HB, they want to combine to give H2 molecule, right? Now what you can relate, how this can combine, so according to linear combination of atomic orbitals, which we can write in short form LCAO theory, linear combination of atomic orbital. So according to LCAO theory guys, what you all can relate, yes, it says that whenever a molecule will be formed, so it will be formed by adding wave function and subtracting their wave function with each other, means by doing the constructive and destructive overlap. So what you can relate, that molecular orbital can be formed by the addition of wave function and it can be also formed by the subtraction of wave function. Okay, Okay, hi Akash. So basically what you can relate is that, like, suppose with the molecular orbital, it can be of two types. How we can relate, let's just discuss. So molecular orbitals is of two types. Good evening. What are those types? It can be a bonding molecular orbital or it can be a no anti-bonding molecular orbital. It can be bonding molecular orbital and anti-bonding molecular orbitals. Very good. Now, how bonding molecular orbital is formed? It is formed by the constructive overlap of atomic orbitals. Now, what is the meaning of constructive overlap? We'll discuss. And anti-bonding is formed by the destructive overlap of atomic orbitals. Now, what is the meaning of constructive and destructive? Let's just relate that. Okay, so remember that constructive overlap is when two same faces comes and combines. Okay, so remember that whenever two same phases comes and combine, like I can tell you, we can relate for one atom, I can relate as a wave function, say psi A, and another wave function psi B. Okay, so if remember that if a positive, like we can relate a crust, we can denote with the positive sign, and trough we can denote with the negative sign to just distinguish them. Okay, so if the positive crust and crust will combine together, positive is approaching positive, the wave function. So what will happen? It will be a constructive overlap. Okay, so when same phases combine, it causes a constructive overlap. So here remember psi A plus psi B will occur, and how it will, you will see that the overall amplitude will increase. So what happened over here? That constructive overlap has taken place. Okay, yes, like both positive or both negative. So remember that when same phases overlap, absolutely Akshay, when same phases overlap, it causes constructive overlap. Very good. Like positive with positive and negative with negative, they are combining, it will cause constructive overlap. But if you will have the opposite, right, opposite wave functions, they are combining, so it will cause a destructive overlap. Like for example, suppose a crust is approaching a trough, like this two wave functions are combining. Okay, positive negative, and here like this it is combining. So what will happen if two different phases are coming? So it's not like the charges, guys, remember, do not need to, like, you don't have to think like opposite charges so like repel each other. Why they are not like opposite charges, they attract each other, same charges repel each other. Why it is not happening like this? So it's not the charges exactly, it's just a representation. Okay, for a crust and trough. So what you can relate in this case, what will happen? You have say psi A and psi B, but they are coming with the opposite phases, positive and negative, like the opposite phases. So what will happen here? There will be a destructive overlap. So overall magnitude has decreased. Now depending upon positive was more or negative was more, you will get the wave accordingly. Are you getting this, guys? So here psi A minus psi B has occurred because what happened here? Destructive overlap has occurred. Absolutely, right? Yes. So what we can relate? This is a destructive overlap. Very good, Akshay. So this is destructive overlap, means when opposite phases combine, it causes destructive overlap. Like positive negative positive means crust with trough with crust, like that. Okay, so how we can relate? It's very simple. So whenever you're showing any orbital, like we can discuss that. So you're showing any orbital, say 1s with 1s. What we can relate here, guys, that both 1s when they are combining, so we know that they are spherical in shape, right? So when they are combining in such a manner that they are approaching together with the same phase, So what will happen? They will combine together and they will form a sigma 1s bond, which is considered as bonding molecular orbital. But suppose they are combining with the different phase, positive, negative, both possibilities are there. No, both possibilities are possible. So always for every atomic orbital combination you will get one bonding, one anti-bonding, one bonding, one anti-bonding, like that you will get. So what will happen? They will undergo destruction and you will get sigma star 1s. So remember that star we use to represent anti-bonding molecular orbital, and without star it is bonding molecular orbital. Very good. So like that, 1s 1s you can relate, 2s 2s, 2p 2p. Right now 2p 2p has how many? Like if I relate, we have 2p plus 2p. So 2p has px, py and pz, right? All are there because when we make a 2p subshell, it has a dumbbell shape, right? And it contains three orientations, px, py, pz, right? How many of you guys know this? So basically then what will happen? Px will combine with px, py will combine with py, pz, like depending upon same phase and different phase. So what is going to happen here? 2p and 2p are combining. So total how many molecular orbitals will be formed? 3 molecular orbitals are combining. So total how many molecular orbital will be formed? 6 molecular orbitals. Are you getting that? Because this is 3 atomic orbitals and this is also 3 atomic orbitals. Because it's p, 2p, but it contains, 2p is a subshell. 2p is a subshell, but it contains 3 orbitals, px, py, pz. So 3 atomic orbitals it will combine, it will cause 6 molecular orbitals. Now let's just quickly talk about it, how we can relate with it. So you'll be able to relate better. So remember that guys, when we write atomic orbital configuration, how we write it guys, tell me. How we write atomic orbital configuration? We write like this way. Atomic orbital configuration, how we write it? We write it as 1s, 2s, 2p, 3s, 3p, 4s, 3d, like that, so on, right? Now for molecular orbital configuration, how it will be? Because for molecular orbital your 1s and 1s will combine, so it will give you sigma 1s, sigma star 1s. Same way 2s and 2s will combine, it will give you sigma 2s, sigma star 2s. Okay. Now after this, how the configuration is going to be, it depends upon the number of electrons, how much it is present. Okay, very good. So what we can relate, a simple thing, that how it will be. So it can be the configuration, it can be followed depending upon like you as you said, Aufbau principle or n plus L rule we can relate. But here obviously we are arranging the atomic orbitals on the basis of increasing in their energy, like from lowest to the maximum energy we are arranging them. But here the configuration can be little different, like because when your, let me tell you, when your what, the x and like 2p 2p orbital will combine. So you have the first orbital will make sigma bond, after that it will be making pi bond only. So what happens, or depending upon energy when we place it, so it can be pi 2px, pi 2py, then it can be sigma 2pz, yes, it can be pi star 2px, pi star 2py. So what I'm doing, I'm arranging them on the basis of what? On the basis of their increase in energy, or the Aufbau rule. So molecular orbital configuration, it is this. When we write till nitrogen, so from hydrogen to nitrogen molecule guys, remember you have to write the molecular orbital configuration like this. How you got it? When the atomic orbitals combine, they give you molecular orbital. And now what we are doing, we are talking about the molecular orbital, and that too what it follows, we can discuss that in the saline feature. So we discuss only 3 features. Now 4th 5th features let us discuss quickly so that we can relate. Always remember that your molecular orbitals, they follow Aufbau principle, Molecular orbitals follow Aufbau principle. It also follows Pauli exclusion and Hund's rule. All the principle it follows. So molecular orbital follows, yes, Aufbau rule. Very good, Akshay. Then it follows Pauli exclusion and also Hund's rule. So your molecular orbitals follow all the rules. Aufbau, Pauli exclusion, just like atomic orbitals, it follows all the rules. And remember, any molecular orbital, any MO can accommodate maximum 2 electrons. Can accommodate maximum 2 electrons. Okay, guys? Very good. Absolutely correct, Akshay. Good. So remember that. And one more thing, that whenever you write molecular orbital configuration, so in the atomic orbital configuration, we used to take all the number of electrons which is there present in an atom. In molecular orbital, we'll discuss the molecular orbital configuration. We'll be taking the total number of electrons present in a molecule. Okay. So MO configuration is written with total number. Is written with total number of electrons present in a molecule. Okay, so these are some saline features. So I gave you this configuration, molecular orbital configuration, which we get on the basis of linear combination of atomic orbitals, and how they combine, that we got to know. So depending upon that, we can talk about many of them. Okay, so basically what we can relate, we discussed that hydrogen to nitrogen molecule. I'll tell you what is the reason that we have a different configuration. So hydrogen to nitrogen, we have a different configuration, sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. Then you have pi 2px is equal to pi 2py. Then you have sigma 2pz, because they all are forming from the 2p orbital only. Then pi star 2px is equal to pi star 2py. And then you have sigma 2pz star. But what happens when we saw oxygen to neon molecule? So we are talking about mainly centric molecules, or we are talking about only the molecules which are made from same atoms right now. Okay, so what you can relate in that case, guys, here from oxygen to nitrogen, the configuration was found to be little different. What is the difference? Let's just see. Sigma 1s, sigma star 1s, then sigma 2s, sigma star 2s. Then after that, what you get is, you get sigma 2pz before. So sigma 2pz, then only the sigma 2pz, and this changes the position. So then you will get pi 2px is equal to pi 2py on the position of it. When I write equal means they both have same energy. Then I will get pi star 2px is equal to pi star 2py. And then sigma 2pz star. Okay, guys. Now, what is the difference over here? So, if I talk about in the nitrogen, what configuration if you have 1s2, 2s2, 2p3 for the one atom till nitrogen, your p orbital doesn't start undergoing pairing. Here, till nitrogen, p orbital doesn't start doing pairing. But in oxygen, what happens? Your p orbital start undergoing pairing. And because of this reason, there is found a difference in the configuration. So remember that hydrogen to nitrogen, what happens? Pairing doesn't start in p orbital. Pairing doesn't start in p orbital. Doesn't start in p orbital, and because of this, there is no much repulsions, and s and p orbital mixing takes place. But from oxygen to neon, what happens? Because pairing starts taking place in p orbital. Pairing starts taking place in p orbital. And because of this reason, guys, yes, sp mixing doesn't take place. S and p orbital mixing doesn't take place. And that is the reason that you can relate. In short form, I have given you. If you will be checking in many books, you'll be scratching your head that what is the reason, how this is possible, how this is coming. So like that, you can relate. So basically, oxygen to neon, pairing starts taking place in p orbital, and that's how you can write. So this is a difference in the configuration. Very, very important, guys. All of you guys should know it. Okay, so we are not talking about molecular orbital diagram at present. We are discussing now the configuration, how you will write. Suppose you have to write for hydrogen molecule. So hydrogen molecule, there are total 2 electrons. So you will write sigma 1s2. If you have to write helium 2, although it doesn't exist, but suppose if you have to write it, how you will do that? There are total 4 electrons. You will write sigma 1s2, sigma star 1s2. You will just fill that. Then suppose Li2. So it doesn't exist, but specifically we can relate sigma 1s2, sigma star, because it will have 6 electron. Then sigma star 1s2, sigma 2s2. Like that. Okay. So that way we'll be doing. Like suppose if I tell you what will be the configuration of nitrogen, which contains 14 electron. So what it will be? Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. So 8 electron I have filled. I have to fill more 6 electron. Then after that, what comes? Pi to px is equal to pi to py. Then sigma to pz, pi star to px is equal to pi star to py. Like that it comes, right? So what you can relate? Already 8 electrons are filled. I will fill more. 9, 10, 11, 12. Now why I have filled them first half and then full? Because they both have same energy. So first I should make them half filled, and then only I can make them fully filled. Okay, so you will fill the electron here 2 to 4, 6, 8, 10, 12, 14. So total 14 electron filled. So this is the configuration for it. If you want to write for oxygen, oxygen contains 16 electron, but what will be the difference in configuration? You'll have sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. Now the position will change. Sigma 2 pi z will come first, and then pi 2 px is equal to pi 2 py. And then sigma 2 pz star. Then pi star 2px, pi star 2py, and last sigma 2pz star. Correct? Yes. Pi star 2px is equal to pi star 2py, and then sigma 2pz star. So you can fill this 16 electron 2 to 4, 6, 8, 10, 11, 12, 13, 14 and 15, 16. So like that you will be getting it. So like this you can write configuration of any of the given compound. Okay, if you want to know learn the trick behind how to make the molecular orbital diagram, guys, so you have to put a comment in the comment section, and then I'll be helping you. Okay, so what is the benefit of writing this configuration, guys? So let me tell you some applications also for it, some really important application. So one of the application is it helps to find out the bond order. It helps to calculate the bond order. Means how many bonds are there in between two atoms. How you can find it out? The formula is half NB minus NA. So bond order you can get it by the formula half NB minus NA. NB is number of bonding electrons, and Na is number of anti-bonding electrons. So if we'll count for the oxygen, how many number of bonding electrons are there? So it is 2 to 4, 6, 8, 10. So total 10 are the bonding electrons, minus how many are the anti-bonding? We can count. There are 2 to 4, then 5, 6. There are 6 anti-bonding electrons, right? Very good. So 10 minus 6, what you will get? You will get half into 4, which is 2. And we all know that in between oxygen there are 2 bonds. So this is how you can find it out and specify that what is the bond order. Now if we get to know bond order, what is the benefit? So remember always, guys, that your bond order is directly proportional to bond stability. Means more will be the bond order, more will be the bond stability. Your bond order is directly proportional to bond dissociation energy. Okay, and also remember this is bond order is inversely proportional to bond length. So they can give you any comparison and you can solve it. It's very simple. Okay, guys. Now second application, one more I will tell, that it helps to find out it helps to find magnetic character of molecule. How you can find it out? It's very simple. In the substance, if you have a any substance which we have, it can be either paramagnetic or it can be diamagnetic. How I can relate which one is paramagnetic? So the paramagnetic will be the one which contains, or the paramagnetic means the one which gets attracted towards magnet, a substance which attracted towards magnet. And why it is attracted towards magnet? Because it contains unpaired electron. So diamagnetic is doesn't attract it towards magnet. Why paramagnetic substance? Because it contains unpaired electron, so you can check the configuration, and here it doesn't contain unpaired electrons, it all are paired, so that will be diamagnetic. Like for example, if I say oxygen is paramagnetic, guys, it gets attracted towards magnet, you can see that there is a unpaired electron. And if I talk about your nitrogen is diamagnetic because it doesn't have any unpaired electron. Unpaired electron means when it is single, only one electron is there, it's unpaired. When two are there, it's paired. Okay, very good. So what we discussed today, guys, we discussed very quickly, although MOT is a very big topic, but in short, we discussed about how we can understand what is MOT, what are who gave it, what are the saline features of it, how we combine atomic orbitals, what is the molecular orbital configuration, and what are the applications for it. In a very short time, like in a half an hour, we discussed about all the things, right, in a short and crisp manner. So I hope all of you understood it. Yes, make sure you are revising it and solving few questions related to it. If you are not able to get it, you can put it in the comment section and we'll be discussing that. Okay, so yes guys, I want to give you one small information, like the classes that we have on YouTube, same way we have classes on our Unacademy app as well. So on Unacademy app also you can join the classes, which is absolutely free. There are special classes which is at the same time 6:30 to 7:30 p.m. Okay, mostly like most of the days for 11th and 12th, both it is there alternatively. Monday, Wednesday, Friday it is for 11th, Tuesday, Thursday, Saturday it is for 12th. The special classes which are absolutely free, so you guys can join even there as well. So yes guys, so okay, we'll be meeting in the next session then. Thank you all of you. Bye bye guys. Thank you everyone. Bye Akshay. Bye everyone. Thank you guys.